Welcome again to another action-packed episode of Empowering Introductory Algebra. Hi, I'm Bob Young, Assistant Professor of Mathematics at Brevard Community College. Along with my excellent support staff of WBCC, we continue to bring you top-notch algebra lessons that you can work on anytime convenient to your busy schedules. Let's continue our journey. Now, in our last lesson, we were talking about the LCM and LCD of rational expressions here because we are going to begin to add and subtract these polynomial fractions in this episode. So let's go back as a quick review to the graphic here. And we noted that to find the least common multiple or least common denominator, we're going to factor the denominators if necessary and break all numbers into prime numbers or factors. Multiply each by the greatest number of times that it appears in any one factorization. All right, so make sure you get that in your notebook, and let's go back to the example we left off on. So we found the LCM of 28, 42, and 60 by breaking these what are called composite numbers into prime numbers, and then taking the most of each prime number and multiplying it together to get the LCM. All right, so we're going to continue that thinking. But, oh, no, Young, not the variables, yes. Now, some of you think variables are difficult, but actually they're easier than numbers because let's look at these three here. We've got three monomials, and we want to find the LCM of them. So all you have to do is ask yourself, gee, which one has the most x's in it? It doesn't take Einstein, does it? No. Yeah, this one, x to the fourth. Which one has the most y's? Y to the fifth power is the most number of y's. So variables are very nice to get the LCM. You just take the most of each one and multiply it together for that answer. How about that? Yay. All right, next ones. I gave you three monomials, but I threw some numbers in there. Now again, notice all of these are not prime numbers, so let's make the 6 into prime by breaking it into 2 times 3. So that's kind of a nice one to prime up. 18, I'll come over here and keep dividing by primes, cut it in half. 2 goes into it 9 times. 9 is not prime. 3 goes into it 3 times. So the prime factorization of 18 is 2 times 3 times 3. So I wanted to kind of tie together variables and numbers, getting the LCM, because that's going to be a very important creature down the line here. So now let's look at these three monomials now that I've got the numbers broken into primes. Which one has the most 2's in it? Well, they all have 1, so 1, 2 goes into our LCM pot. All right. Which one has the most 3's? The 18 has 2. So we'll put that into and stir it up here real good. Which one has the most a's? We'll go to variables now. 2 a's in the first monomial, so we'll put a squared in there. And which one has the most b's? 2b or not 2b over here, b squared. So when we multiply the numbers together, the LCM of 2a squared, 6ab, 18b squared would be 18a squared, b squared. All right. So getting the LCM or LCD of its fractions, not bad. Let's increase our understanding. Now, I gave you some binomials and asked you to get the LCM. Don't panic. All right, so to get the LCM of these, we're going to have to do some factoring. Now, how can I factor this first binomial? Well, take out what's in common, which is an n squared. And when I take the n squared out, what am I left with? You know it, n squared minus 1. Now, am I done factoring? No, because, the difference of squares there. Yes, there they are. So we can break the difference of squares apart into nn plus minus 1, 1. All right, so now we have this binomial completely factored by taking out that greatest common factor first and then factoring the difference of squares. On the second binomial, we can also take a common n squared out, and that leaves us with just n minus 1. All right, so now that we have both of these completely factored, we're going to find that LCM. And how do we do it? Well, we take the most of each thing and multiply it together. Even quantity-wise it works. So which one has the most n's by itself? Well, I see an n squared in common in both of these. All right, what else is in common? Well, n minus 1s are in common. How many? The most in either one of these two is 1. And there's something else we need, an n plus 1. So the most n plus 1s, although this is the only one that has 1, gets thrown into our LCM pot. And there is the LCM of these polynomials. Yeah. All right. And then I went from binomial examples to trinomials. All right. We can also find the LCM of these guys. So let's go ahead and factor. So remember, when the numbers weren't prime, we broke them into primes and we took the most of each one and multiplied together to get it. When they're polynomials, we factor and we take the most of each one. All right, so this one would factor into xx, factors of 6 that will give me 5, and they both have to have the same signs here. It would be minus 2, minus 3, so that's a nice trinomial to factor. This is a trinomial square. I would factor and get x minus 2, not once, but twice. All right, so to get the LCM of these, now that I have them factored, ask yourself, all right, self, which one has the most x minus 2's in it? This one. How many? 2. So we'll write x minus 2 quantity squared. And what else do we need? The most of the x minus 3's, which is only 1. Put them in the LCM pot. There's your answer.